Consider this braced column, which is fixed at one end and restrained by a vertical roller at the other. Well, when this column is subjected to a compression load and reaches unstable equilibrium, it has this buckled shape where the column remains at a right angle to the fixed support and rotates at the top. And it thereby develops a reaction at the roller, and you'll have an equal and opposite reaction at the fixed support and a vertical reaction to resist the compression load, and also a moment reaction to restrain the column from rotating at the fixed joint. So if the column has a length L, then taking moments about the fixed support, the moment reaction is the reaction at the roller by the length of the column. And here we take our x coordinate in this direction, and taking a free body off the bottom of this column, when it's in unstable equilibrium, we have a shear force and a bending moment. And if we take moments about this point, then we have the bending moment plus the reaction by the perpendicular moment arm, which is x, and P also causes an anti-clockwise moment, and that's multiplied by the perpendicular moment arm, which is the lateral displacement at this point, and then minus the moment reaction, which is clockwise, so that will be RR by L, and that's equal to 0. And writing the bending moment in terms of the curvature, which is the second derivative of the deflection with respect to x, plus PV, and then we'll take the reaction terms on the other side. So that will be L minus x. And now we can divide through by the bending stiffness. And a solution to this equation is a superposition of the homogeneous solution, which is a sine lambda x plus b cosine lambda x, where lambda is the square root of the compression load on the bending stiffness, and then we superimpose this with the particular solution, which can be obtained using the method of undetermined coefficients. And now we can differentiate this equation to get the rotation. And we know that the displacement at the fixed support is 0. So that gives 0 is equal to B plus RR on P by L, which we can solve for B. And we also know the rotation at the fixed support is 0. So we get 0 is lambda A minus RR on P. So therefore A is the reaction on P by lambda. And at the roller, which is at x equals L, the displacement is also 0. So what we get is 0 is a sine lambda L plus b cosine lambda L. And here we have RR on P by L minus RR on P by L is 0. And if we substitute for A and B in this equation, using our previous boundary conditions, and cancel out RR on P, then we get 1 on lambda sine lambda L is equal to L cosine lambda L. So if we divide through by cosine lambda L and multiply through by lambda, we get tan lambda L is lambda L. And now we can plot this. So we have lambda L on the x-axis, and this here is tan lambda L, and this here is lambda L. We're looking for the smallest positive value of lambda L that satisfies this equation, and that's 4.493, which you can obtain numerically. So if you substitute for lambda, which is root p on EI, divide through by L and square both sides, you'd get p on EI is 4.493 squared on L squared. And this is actually the critical value because we took the smallest possible value where this equation was satisfied. And now we can multiply through by EI to get the critical buckling load. But we want to put this in the form of pi squared by EI on L squared. So we have some unknown value alpha by L in the denominator. So therefore this equation gives 4.493 squared is equal to pi squared on alpha squared. And then if you solve this equation for alpha, we get 0.699. So therefore the critical buckling load is equal to pi squared EI on 0.7 L squared. Please subscribe, like and comment to help me reach more students.